Hey scientists! When scientists deal with science, very often that involves looking at number. Sometimes those numbers are just normal sized numbers, and other times they're really large or really small. We've been looking at astronomy, so the study of space, and in astronomy the numbers tend to be really large. Fortunately for us, scientists have invented something called scientific notation. Scientific notation is a way of writing very, very big numbers or very, very small numbers in a way that's a little bit easier for us to see. And I want to start with just a smaller example. When we change a regular number, which is usually rounded off or ends in zeros, a lot of zeros, when we want to change a number like that into scientific notation, we move the decimal place up until it is a one-digit number. So in this case, our number is 7. And then we count the zeros, or we count the number of times that that decimal place has moved. In this case, it's 2. Then we'd say 700 is equal to 7 times 10 to the power of 2, to represent 2 zeros. You can also write it like this, 7 times 10 to the power 2. It means the same thing. Alright, so that's a nice small example. I could do it with a bigger number, let's say 6,000 equals 6 times 10 to the power of 3, because I have moved the decimal place 1, 2, 3 times to turn that into a 6. What happens though if there's more than one number, so a mix of zeros and numbers? Let's go with 750 as a start. If I have a number like 750, I would still move the decimal place up twice. So it's going to go 1, 2, and that's going to be 7.5, and I've moved it, remember, from here, 1, 2, I've moved it 2 places, so it's still times 10 to the power of 2. Just like if I had 6,900, that would be the same as 6.9 times 10 to the power of 3. Can you see that that could be useful? Can you see that that could be useful? See, my face is in the way. In dealing with really large numbers, right? And so I just want to do one more example with decimals, because I think that might be helpful for you before I move on to the Earth and the Sun. Let's do another one. Let's do a big one. Let's say 682, and let's do 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is starting to get into the realm of the size of numbers where scientific notation is useful. Remember, when we do scientific notation, I start with one digit, which is 6. The rest comes after a decimal place, 0.82. And I want to see how many times I've had to move the decimal place to get from the end of this number right to the beginning. So I'm going to count from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 6.82 times 10 to the power of 11. And that just means if I was to expand that number out, I would move this decimal point 11 times. You might say, Mr. Honeybun, that is confusing. Why would I bother? But guys, this can be really useful for very, very large numbers, and I'm about to show you an example of that. Let's go down to my Earth and Sun. Alright, so here I've got Earth and Sun, obviously not to scale because the Sun is much larger than that in comparison to the Earth. And the distance between Earth and the Sun in kilometers. You might know that the distance between the Sun and the Earth, let's go blue, is about 149.6 million kilometers. Million kilometers, right? And if I was to write that out as a number, it would look something like 1, 4, 9, 6, and then 3 zeros. My challenge now is to turn that fairly large number into scientific notation. And so remember, 149,600,000 kilometers. I'm just going to start with the 1, so this equals 1.496 times 10 to the power of something. To figure out what that something is, I'll start here, and I'm going to count 1, 2, 3, 4, 5, 6, 7, 8. 10 to the power of 8. That is how many times I'd move that decimal point. Let's go with an even bigger number. So let's say with the mass of the Earth in kilograms. I'll zoom a little bit into the Earth here. So the mass of the Earth in kilograms. Now we're getting really, really big. First I'm going to attempt, I might have to zoom out again. I'm going to attempt to write that number for you because we're getting huge, guys. I've got it written down here. I'm going to copy it down. It is this big. 5, 9, 7, 2, and now I get to zeros. I'm going to count to 21. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, just fit. Whoops. Kilograms. That is the mass of the Earth. This kind of number is where this scientific notation is really useful, right? Really, really useful. So remember to write this in scientific notation. The number up here is equal to 5. So I pick the first digit, 0.972 times 10 to the power of something. You might think it's to the power of 21, and you would be wrong. It's not to the power of 21 because whilst there are 21 zeros, I have to include the 3 digits here. So if I was to jump my decimal place, I'm going to count by 3s because that's how my number is organized. If I was to jump my decimal place, I'm going to count how many decimal places, right? Skip counting by 3s. 3, 6, 9, 12, 15, 18, 21, one more, 24. So the mass of the Earth is 5.972 times 10 to the power 24 kilograms. That shows me that I would move the decimal place 24 times in order to show that number in its entirety. But for this example, it's certainly a lot easier for me to write this than to write out that full number with all those zeros. So guys, when you come across stuff like that, usually just like that, 10 to the power of 24, hopefully that makes more sense to you. Scientists can also go the opposite way by putting a negative sign on the power, but I'm not going to go into that. That would be used for really, really small numbers, like in chemistry and biology.